These are the notes for AP Calculus on the topic of volumes with a flat base and known cross sections continued. So this one we're going to look at with the calculator, and it's a little bit different. It says let f be the function defined by f of x is a piecewise function, 1/3 x plus 3 squared, or negative 3 less than or equal to x, less than or equal to 0. So this piece here, you can see goes from negative 3 right here, where x is 0. And then the breakpoint's at 0. You can see the second piece is 3 minus 3 sine of the cube root of x on the interval from 0 to pi cubed over 8. So that's this interval here. And we'll talk about where that strange value of pi cubed over 8 comes from there. So on this one it says region R is the base of a solid. Let region R be the region bounded by the graph of f. So there's the graph of f, it's two pieces, and the x-axis. So there's no region enclosed yet unless you include the x-axis there. So there's our region enclosed right in there. Okay? But we're not revolving it around anything. Instead it says region R is the base of a solid. So we have this completely flat base, this region R right here. And for this solid, each cross-section perpendicular to the x-axis. So the cross-sections are perpendicular to the x-axis. Here's our x-axis right here. Perpendicular, that means it'd be going vertically like that with dx. And you could also say parallel to the y-axis. That would be the same thing. But usually these are worded in terms of what they're perpendicular to. So perpendicular to the x-axis would be like this. But notice what's different about this one is, unlike most regions here, this rectangle starts off between the red piece of the piecewise function and y equals 0 here. But if we keep going, notice that's not always the case. Over here it's between the second piece, the blue piece of the piecewise function, and the x-axis. So because of that, we actually need to split this into more than one integral. Because this base here is different than this base right here. They both involve a different piece of the piecewise function. So whenever the rectangle doesn't always stay between the same two curves, then that's when you'll need more than one integral to figure it out. And then it says we've got an isosceles right triangle with a leg along the base. So this one, to figure out what that formula would be, we draw that out here. Got an isosceles triangle. Move this a little bit so it's a little more isosceles here. There we go. The right isosceles means two of the sides are equal here. In this case, with the right triangle, it's the legs that are equal. So the base here, this length here is where this says a leg is along the base instead of the hypotenuse. So you can picture we've got this isosceles right triangle poking out of each of these rectangles here. This represents one of them that's poking out the page there at you. You can see the largest one would be right here at x equals 0. You know, this large right triangle, isosceles right triangle right there. So in this case, since it's isosceles, we know the height has to be the same as the base of this plate, so the height is b also. So the area formula would be 1/2 b squared. 1/2 base times height, 1/2 b times b. So that's the formula we use, but we'll need two integrals. So this 1/2 is a constant, I can go out in front. And then the first integral would be from negative 3 to 0. That's where that one stops at. We're split into two. We're basically split into it right here. And the base that's going to get squared is the top minus the bottom. When you have a vertical distance like this. So the one on the top is this 1/3 x plus 3 squared minus the one on the bottom, notice is just 0. y equals 0. But then that gets squared. Now the reason why we're using the area formula is because what turns it into volume is when you multiply by the thickness dx. That's what makes it volume instead of just area. So we're adding up all those all those isosceles right triangles, those really small ones right over here, and they get larger and larger as you head this way until the largest one is right there at 0. So that'll give us the volume up until x equals 0. But the region keeps going all the way here. So we'll have plus, also we'll have same formula because it's the same shape. These isosceles right triangles, so 1/2. The other integral though would be starting at 0, where the breakpoint is, and we've got this pi cubed over 8. So let's see where that's coming from. Well, if we substitute that into this function, let's see what happens. We get 3 minus 3 sine of the cube root of pi cubed over 8. And if we simplify that, cube root of pi cubed over 8, well, the cube root of pi cubed is pi, cube root of 8 is 2. So that really becomes the sine of pi over 2, which is just 1. So you end up with 3 minus 3 gives you 0. So that is in fact exactly where the region stops there, where it intersects the x-axis. So that would be our upper limit, pi cubed over 8. And the base here, though, is going to be different as well. The base, the top minus the bottom here. The top one here is this piece. 3 minus 3 sine cube root of x. And then I get squared again, because the form is 1/2 the base squared. And then times dx. So notice all this we were able to set up on this part without using the calculator. But now in order to integrate it, that's where we'll need our calculator to make this a little more manageable. So let's go ahead and enter this in both the 84 and the Inspire. Let's start with the 84. So I've got 1/2, or you could just put 0.5. And then math, number 9, function integrate. And then what we want to integrate is this expression here. So you just got to be careful with your parentheses. This first parentheses is for the integral function, and then we need this open parentheses in green here. And then 1/3 right there. I'll put the 1/3 in parentheses. So another open parentheses, 1/3. And then an open parentheses for the x plus 3. Close parentheses on the x plus 3. And then squared. Then we need a close parentheses here so we can square that whole thing. And then comma x. The other option is you could actually square it out and get 1/9 x to the 4th would be the same thing. X plus 3 to the 4th, I should say. Either way. And then comma, lower limit's -3. Use the negative with parentheses out front. Comma, upper limit is 0. And then close parentheses on the integral function. That'll give us the volume up until the y-axis there for this part. And then plus 0.5, again 1/2. And then we've got the integral. So math, number 9 again, function integrate. And again, we need these parentheses in green here first. So open parentheses, 3 minus 3 sine. You can either write as x to the 1/3, or it might be a little simple, the cube root on this calculator if you hit the math button. And then go down to number 4. Notice 5 is any kind of root, but 4 is a cube root specifically of x. Then close parentheses on the cube root. Then close parentheses on sine. Then close parentheses on this whole expression so we can square it. Then comma x. Comma lower limit is 0. Comma upper limit is pi. You can either use the caret button 3, or if you hit math again, you can see number 3 is cubed divided by 8. Close parentheses, and then enter. And sometimes on these, especially the ones with the roots, they can take a little while to integrate. So we get 11.425. Just make sure that's correct. Let's check on the Inspire. I think something's a little off there. I don't see what I typed in wrong there. All right, let's check it on Inspire, see if we get the same thing here. And I'll come back to that one if it's not right. All right, so calculate. So let's start with a new document. Add calculator. And then we'll enter 1/2, you can put out in front, or 0.5. This one looks more like the newer 84s also. Integral from -3 to 0. And then open parentheses, 1/3. Open parentheses, x plus 3 squared. And then there's a squared on the outside here. Dx. And then hit the right arrow so you're out of that integral, plus 1/2. And then right next to the 9, the integral from 0 to pi cubed over 8. So pi is right here. Cubed. Oops, let's put this in a fraction here. Over 8. And then we had open parentheses, 3 minus 3. Trig sine of the cube root. You can use this nth root here. Cube root of x squared dx. Yeah, that's what the answer should be there. 3.340. So let me go back to the other calculator and see what we did wrong there. So let's write it down there. You wrote up 3.340. If you want to remind yourself it's volume, you can put units cubed. I think I might have forgotten the squared on the other one. Let me just check here. So on the 84, let's see if I did forget that squared there. No, I had that squared. Let me take a look carefully again. So we've got 0.5 integral 1/3 x plus 3 squared squared x -3 to 0 plus 0.5 3 minus sine cube root of x squared, whoops, x comma 0 pi over pi cubed over 8. Let's see what's causing that here. I'm going to look at it side by side with the other calculator. Sorry about this. Unless I typed something wrong, I just don't see it for some reason. Check my mode here. It's in radians. So second entry. Just don't see what it is here. Go back to the one on paper here. Sorry, if you figured it out, you can fast forward through this part. Just trying to figure out what went wrong when I typed it in. Oh, I found it. Okay, sorry about that. I forgot the 3 in front of the sign here. So I'll just insert that right here. So when you make a mistake like that, go second INS 3. I just accidentally left out the 3. For some reason I didn't see it there. Enter. And now it should give me the same thing. There we go. Okay. Sorry about that. Sorry it took me so long to find my careless mistake there. All right, now let's take a look at part B. So then for part B, now it says region R is the base of a solid. For this solid, each cross-section perpendicular to the y-axis. So perpendicular to the y-axis, here's our y-axis perpendicular to that. That tells you we need a horizontal rectangle with dy. But when we draw that, unlike the vertical rectangle, notice no matter where you draw that horizontal rectangle in this region here, it always stays between the blue and red curves at different pieces. So we will not need to split this into more than one interval since it stays between those. However, when it's dy, notice this one's a semicircle. So remember the area formula we derived for a semicircle was pi over 8b squared. And where this is our base here. But since it's dy, everything has to be in terms of y. So the lower and upper limits are y coordinates, and each of our pieces here, the red and blue piece, Because remember, this is less like y right now, y equals. We need to get those both solved for x in terms of y. So let's say we start with the red piece here. That piece is y equals 1/3 x plus 3 squared. So to solve that for y, we could first multiply both sides by 3, wipe out the 1/3 there, so it'd be 3y equals x plus 3 squared. And then to get rid of the squared, you can take the square root of both sides. Now initially, you might think you need plus or minus there. But notice the y coordinates here are positive above the x-axis, so it's just going to be the positive one. So it's the square root of 3y equals x plus 3. And then just subtract the 3 over. So you get square root of 3y minus 3 equals x. Okay, so now we solve that one for x. And then the other one, this is again y equals 3 minus 3 sine cube root of x. To solve this one for x, first you can subtract the 3 over. Y minus 3 equals negative 3 sine of the cube root of x. Then divide by the negative 3. You get y minus 3 over negative 3 equals sine of the cube root of x. And then to get the x out of the sign, you would have to take the arc sine of both sides, which you can write as arc sine, or in this case it might be easier to write, just like it is in our calculator, as sine, looks like a negative 1 power, that's the same as arc sine, y minus 3 over negative 3. And arc sine is an inverse of sine, so those cancel out, so all that's left is the cube root of x. And the last step would just be to cube both sides. Get rid of the cube root. So on the second piece, when we solve for x, we get x equals arc sine y minus 3 over negative 3 cubed. All right, now we can set up our integral here. So we've got pi over 8 on the outside. We don't need to split into 2, but we have to use the y coordinates of where the region starts and stops. So we've got all these rectangles here. Notice we've got these semicircles coming out of the board at us. The largest one will be right here on the x-axis, and they get smaller as we head to these really tiny semicircles right here. Then, so we have pi over 8 on the outside, but where it starts is right here at y equals 0. That's where our x-axis is. So the lower limit is 0. And notice it stops right here where y is 3. So we're integrating all those semicircles from 0 all the way to 3. And then it's going to be the base squared. So this whole thing is squared. But just like when we do a vertical distance, it's top minus the bottom. Just like with the shell method, when you have a horizontal distance, you go right minus left. In this case, the one furthest to the right is the blue piece, which we solved. So that would be the arc sine y minus 3 over negative 3 cubed minus the other one, since there's two terms, it'd be in parentheses as square root of 3y minus 3 squared. And then this whole thing, that's our base, right minus left, because the one on the right has a bigger exponent. I get squared because it's pi over 8b squared, and then times dy. Principle of the ball. All right, so when we work this on our calculator, let's put it in our calculator for both of them. Start with the 84. So pi over 8, we can put that out in front in parentheses. And then math number 9, function integrate. And then we got to be careful with the parentheses. So we first have this open parenthesis. Well, this parenthesis here is for the integral. Then we have an open parenthesis, the green one, that's going to get squared eventually. Then we have another open parenthesis in the blue there
for arc sine, which you go second on sine, it's arc sine right there. And then inside arc sine, we've got y minus 3 over negative 3. So this whole y minus 3 has to get divided by negative 3. So we need another open parentheses. However, on the 84 and 83, I don't think there's a way to put in y here, as far as I know. So we're just going to type everything with x. And it's going to give us the exact same numeric answer, because no matter what letter this is in here, as long as it's all the same letter, it'll give us the same answer on our calculator. So it'll be parentheses x minus 3, close parentheses on the x minus 3, and then divided by negative 3 with a negative in parentheses out in front. Then a closed parentheses here, that closes off what was inside arc sine. Then we need another closed parentheses so we can cube math and then number 3 there. So we can cube this whole thing. And then we need minus, then another open parentheses. Oops. I just realized I accidentally put an extra square there. Sorry about that. This one wasn't squared, was it? Just the whole thing is squared, so let's erase that here. That extra square should not be there. Sorry about all the mistakes on this video here. But we're fixing them. So we've got square root of 3y. So second square root of 3x here. Close parentheses on the square root. And then minus 3. Close parentheses. We're subtracting, that's the one in red here, this whole thing. Then a close parentheses so we can square this whole thing. That's where the square goes. And then comma x. Comma lower limit is 0, comma upper limit is 3. See if this one works out. What it's supposed to be. Yep. So 4.592. Again, if you want to put units as volume, it is units cubed. And again, these tend to get smaller answers than the disc or shell method because we're not revolving around and creating this big shape. We're just building these geometric shapes on top of this flat base. Alright, and finally let's just look at putting that in the Inspire. In Inspire you can use x also, or it does allow you to put it in with terms of y here. So we could just put the fraction of pi over 8 out in front. And then our integral from 0 to 3. And then open parentheses since that whole thing is going to get squared. Then another open parentheses where we have arc sines on the trig function. And then you can make it look like a fraction like this, so it's a little easier to type in. And if you want to use y, that's fine. So it'd be y minus 3 over negative 3. And there's the close parentheses on that. And there's the close parentheses on the arc sine, which gets cubed. And then minus, and then open parentheses, square root. Look back here, make sure I'm remembering it correctly. 3y minus 3. y inside the square root, then hit the right arrow, minus 3, that's not inside the square root. And then this whole thing gets squared times dy. Or you can put x in all these places and you get the same answer there. Oops. Oops, I accidentally put a times in there, sorry. Let me fix that here. So what you can do here is enter. And that allows you to, oops, let me just copy and paste here. I'm going to do Control C, Control V, and then edit this. I accidentally hit times, I didn't realize that right there. It should just be y minus 3. There we go. Now let's try it. There we go. So we get 4.592. And sorry about the longer than it had to be notes there, but that concludes the notes for AP Calculus on the topic of volumes with a flat base and known cross sections continued.